It's a good one to look at. Alright, this is a 2009 8B, and it's about an equilateral triangle. Okay, an equilateral triangle, three equal uniform rods, each of length 2L and mass M, form the sides of the equilateral triangle. Find the moment of inertia of the frame ABC about an axis through A, perpendicular to the plane of the triangle. So basically the triangle, the plane is going into the board and the triangle is rotating like that, down and across. Is that okay? So it's going to rotate that way. Now, the triangular frame ABC, find the moment of inertia of the frame ABC about an axis through A, perpendicular to the plane of the triangle. Okay, so this is all about the I values, okay, starting off. So, what we're going to do is, we have three rods. Okay, and so we have three rods, and what we're going to do with the three rods is we're going to find the total inertia around A. Now, you can see two of the rods in yellow. Tom, you just keep an eye on this as well when you're on it. Two of the rods are held at their end, yeah? So those two rods are held at their ends. That means that they're 4/3. So we're looking for I total around A. There's two rods that are held at A, at their end. So when a rod's held at its end, it's 4/3 ml squared. That is for a rod of length 2L and mass M, which our rod is. Okay? So it's 4/3 ml squared plus another 4/3 ml squared. The next rod I have to look at is this rod here. It's this one in blue. Everybody happy with that one there? The one in blue? Now, the one in blue is not held at its end. Would you agree with that? It's not held at its end at all. So what we're going to do is we have a choice between two things. What I'm going to do is, because this is an equilateral triangle, I'm going to draw a line going from here to there. I'm going to use the parallel axis theorem to get that blue rod's inertia around the point A. So first of all, you notice that my dot on the line BC is actually the centre of the rod. So therefore, what's the formula when you're at your inertia at the centre of the rod? Anybody? Not half. It's a third. So it's I equals 1/3 ml squared. Is that alright? Now the next thing we're going to do after this is we need to find the length of, I'm going to colour this blue now, we need to find the length of that blue line. So just because it's an equilateral triangle, we can say that that's 2L, that's 2L, that's L, that's L. We call that distance D. Okay? We're going to use the distance D using Pythagoras' theorem. We're going to do 2L squared equals L squared plus D squared, and then we're going to get a 3L squared equals D squared. D equals √3L. Please remember that, it's going to become very important. Okay? So we now do the parallel axis theorem for the blue rod here, the rod BC. So you can say inertia of BC, or rod BC, is going to be, I remember the parallel axis theorem? I can name this dot, I can name it, it's basically di of it's on its own plus md. Oh sorry, it would usually be d, but I've already used d for something. So it's basically I plus, we'll call it mx squared, where x is the distance, the blue line distance above, in between A to C. So I'm going to paint the green now. In those two lengths there is the x value. So we're going to get, this time is we're going to get our old inertia from its centre plus this here. Then we're going to add the two of them together, and what do we get? It's 3 ml squared plus 1/3 ml squared, which should be 10 over 3 ml squared, yeah? 10 over 3. Okay, I haven't got the solutions on me, so I'm just going to assume that I'm doing everything right. Okay, now that 10 over 3 ml squared, it in turn is going to be added above to the, that 10 over 3 only represents the third rod, doesn't represent anything else. So what we're doing there is we're adding that on to the 14 and the other 14, and we're going to get a 18 over 3 ml squared. Hopefully that one sounds familiar. Okay, so okay, 18 over 3 ml squared. Now, for those of you that have done part B's in this before, okay, there's a trick involved, whether it's a square or whatever it is. So I'll briefly go over both variants now. Okay, sometimes you'll have a square, all right, and the square would be, it's a square laminate and it'll be rotated around A. Everybody right with that? Now, what will happen then is, when we're doing this question, and we're also going to link, whichever vertex they say is the axis of rotation, we'll link that to the other side for squares and rectangles alike, okay? And then what we'll do then is, it's only ever a square or a triangle, okay? We never do this with rectangles. And then basically what we'll do is we'll rotate it until they're both in the same, they're both horizontal. What this does is it enables us to calculate the turning moments of a force. Okay? So as an example, if this was a mass M, I'd work that line of action back to here, and I'd say that is mg acting down that way. If there's an mg up here, I bring its line of action down here, so that'll be technically 2 mg acting through the middle. And then you can calculate the distance up the diagonal, and you can use the turning moments to calculate what your h value is of the system. Okay, that's how you do those ones. Anybody who's familiar with 8Bs would have done them already. Now, we're dealing with a triangle this time, or 3 rods. So, what I'm going to suggest this time is, I'll just rescue this here, and take a snapshot. Okay. Okay. So, first of all, why am I even doing this in the first place? Okay. We actually have to set the picture before we jump into the question. So, what we're going to do is we're going to go back to the very top, and we're going to go, the triangular frame ABC attached to a smooth hinge at A about which it can rotate in a vertical plane. Same as part A. The frame is held with AB horizontal and C below AB. Okay? So it's held as shown in the diagram. Agreed? And then release from rest. Find the maximum angular velocity of the triangle in the subsequent motion. Okay, so what's going to happen here, guys? It's going to gain kinetic energy, it's going to lose potential energy. Why is it going to lose potential energy is the first question we need to ask ourselves. So, if you imagine the centre of gravity is somewhere along this line. Is everybody right with that? Now, most of you would be inclined to say, is it not dead centre? Yeah? Why is it not dead centre? That's for a laminate. That's when the full thing is made of the same material all the way through. This is rods. So basically the middle of it is empty. This has the effect of reducing the centre of gravity from what would be in the middle for a laminate further down. Everybody cool with that? Okay? Now, secondly, what is let me see. What is actually going on here? Okay? So we drag that up. Now what happens is, if I fix this at A and I rotate this downwards, so hopefully this will work. Now it doesn't really work, but the picture I'm trying to paint is that if that's the centre of gravity there, the centre of gravity is going to arc downwards like a pendulum. And then the only reason this moves downwards is so that the centre of gravity hits rock bottom. So it can't fall anymore. At this point, we can then calculate what angular velocity is the body moving with. Is that okay? So that's the plan here. So this brings in circular motion into inertia. Okay, so you have to be familiar with circular motion. Okay. Now, what we're going to do is gain in PE. Gain in KE, obviously. Gain in kinetic energy equals loss in potential energy. Okay? So, first of all, what type of kinetic energy do we have here? Is it linear or rotational only? Rotational only. Rotational energy, if I'm correct with this, is a half I omega squared. Okay? Next thing after that is loss in PE, which is loss in potential energy. Okay, so how do we calculate the loss in potential energy? I have to calculate the vertical drop, and see this is the new place of the centre of gravity, yeah? I have to calculate the vertical drop from here to here. Everybody alright with that? Now, a bit of useful information to begin with would be how far is the centre of gravity away from the turning point in the first place? That's what we need to find out. Like the square questions that went after in 2013, 2011. What we're going to do is we're going to turn it side on so that it's horizontal. Okay, so we're going to turn this full triangle here side on. And like so, like so. And what we're going to get is, where is the centre of gravity of the compound body? Okay, where is this relative to A? So this works in the following ways. You got to remember, in rods, where does this mass act? Where does the mass act in rods? Acts through the centre of the rods. So the red dots illustrate where the mg's act through. Okay? We're going to bring those mg's up towards the central line, the central black line, to turn them all into horizontal moments. So basically, I have to calculate what is the length of each one. So, like last time, we had that as this is a L, that's 2L, which makes that root 3. Root 3L, not root 3 over L. Everybody happy enough with that? Okay. Now, once you've done this, what you're going to say next is that well, look, the other ones are the midpoints, aren't they? So there'll be a distance. If I draw that line there, the distance from this point to A, this distance here will be root 3 over 2L. Or you could also do another right angle triangle where you're just going to say instead of 2L you'll have L, and then instead of
you'll have the angle.
Sorry?
You'll have the angle, 60 degrees.
You'd have the angle as well, being 30 and 60 degrees, so you can find out what the bottom one is there. Don't need to use Pythagoras, okay? Now that that's done, we're going to treat this as a compound body and figure out what exactly is going on, okay? So, the key thing to remember is moments of individual parts equals moment of compound body, otherwise known as the MGH formula that we've done several times in the chapter. Okay, so what we're going to do is this. What I'm basically saying is that this body here, which is currently A, and this is mg going downwards, which is a distance root 3 over 2 L away. Would you agree with that? Okay, it's root 3 over 2 L away, and then we've got two of them, so it's 2 mg, because both of them are acting through the same point there. And then there's another one that's a full root 3 L away, and that's mg there. So the individual turning points would be 2 mg times root 3 L over 2 plus, what is that again? mg times root 3 L. And this is where we were yesterday, but we didn't know we were right at the time. And this is 3, because the body added together is a compound body of mass 3 mg, and its center of gravity, it would be there, but because there's a weight at the end, the center of gravity gets shifted somewhere further away than halfway. Okay, so that's why the 3 mg is acting a distance h from the axis A. So that will equal 3 mgh. Remember, it's force times distance away from the fulcrum from junior cert. Now, what you're going to see here, guys, is that the mg's, they weren't necessary anyway. So you'll see a lot of marking schemes just skip that anyway, but I actually like to understand what I'm actually doing. And what you're going to have here is root 3L plus root 3L gives me 2 root 3L. And that will equal 3h. Now, there was a question about d over 3. We were having a debate yesterday about why is the centre of gravity of this system, why was the drop d over 3? Isn't that correct? So why was the drop d over 3? Well, remember, we defined d as the distance from the top vertex to the base BC. Okay? D is root 3 L. Alright? D is root 3 L. Therefore, root 3 L is here. That means 2D equals 3H. H equals 2 over 3D. The centre of gravity of said triangle is a third away from the base. Now, that doesn't explain the drop in height though. Okay, we haven't got there yet. But that's where that would have came from. Now that I've cleared all this, and I know that it's 2/3 of the way down, we're then going to go back to the picture we started off with. I gave you this triangle here, with this held sideways, okay? And that's A, B to C. The book started with a 30-degree rotation, because that's 60 degrees, which is 30 by 30. I'm rotating AB down to this axis here to start off where the book was, or to start off where the question specifically told me to start from. So I go, this is now AB. This guy here has rotated 30 degrees to be here, and then the rest of the triangle obviously is here. ABC, like that. Everybody right with that? Now, how much further can it rotate? How much further does it rotate?
3.
Sorry? It can only rotate another 60. Has to rotate. Don't even look at the full triangle. Just look at the centre part. Okay? Just look at this. Don't even look at the full triangle. Just look at just the way I pictured it yesterday. Look at the red part here. That red part can rotate a full. Never done that before. A full 90 degrees downwards. Yeah.
It's at max velocity then, isn't it?
Max velocity down the bottom then. Okay, and your triangle would end up down here, where the red line represents the black line. Okay, we've already rotated the 30, which means we only have another 60 to go. So here's what I'm suggesting. This 60-degree line here, once again, I'm only concentrating on that line. Oh, just stop. I'm only concentrating on this line here. This line here, where I said the centre of gravity is. Okay, so I'm only going to concentrate on that line. So, and I'm only going to concentrate on the distance d, because all points on that line undergo the same drop in height. Like any point on that diagram, the centre of gravity will drop down a certain height. Okay, so we got to find out what that height is. So I'm just gonna call this x, just for argument's sake, just to make my life really easy. Okay, x is here, and it's going to rotate 60 degrees, and it's going to end up down here, like so. Everybody happy with that? It used to be x, and then it's still x at the end. However, this part here in green is what? What's that part in green? It's x cos 60, which is a half x. Everybody cool with that? X cos 60 being a half x. This means that the height drop is x minus a half x, which is a half x. So this part here, that's your height drop right there. And what does x represent? I already said it, that x is how far away the centre of gravity is from your turning axis. So it's actually a half of 2/3 d, which is 1/3 d. So that's your drop, alright? So, now that you completely understand this whole system, you can obviously do it a lot faster on your own. So the 1/3 d goes all the way back to the top, where we, so the drop in h is 1/3 d. D in turn is root 3 L. And then, once you got all that, you're then ready to finish off your program. A half I omega squared equals mgh. This h doesn't represent the distance over here that you're away from your object. It actually represents the drop in height. It's just really unfortunate that they decided to use h as the distance away from the centre of gravity to the axis of turning, the turning axis. Just really unfortunate. It can be very confusing, know that first hand. Now, what we're going to do with h here is we're going to replace it with mg, 1/3 d, but d in turn is root 3l. So, root 3l. Root 3l divided by 3 is 1 over root 3l. Okay. What's our I value? A half. We calculated I earlier. Somewhere up here. 18 over 3 ml squared. Omega squared. Okay, let's do some cancelling. M cancels with M. That L cancels with the L squared. A half of 18 is 9. 9 divided by 3 is 3L equals 3L omega squared, yeah? Equals G over root 3. Then in turn, omega squared will equal G over 3 root 3 L square root that. Omega equals G over 3 root 3 L. Okay.